Hi there, welcome to lecture 20 of Machine Learning from Data. We're going to begin discussing neural networks, a very popular learning model these days. Okay? And we will begin that whole discussion by first deriving the multilayer perceptron. Now, before we get going, let's have a quick recap. We started with the foundations and the linear models, and then we moved to similarity-based methods. Perhaps the simplest of all methods, perhaps the method that the 5-year-old uses. And in sort of discussing these similarity-based methods, we talked about the k-nearest neighbor algorithm and the radial basis function networks. Okay, so these are very powerful methods. Okay, and in discussing these methods, we found a use for unsupervised learning. Okay, in the k-nearest neighbor algorithm, you have to find the nearest neighbor, and if you store your data in convenient geometric structures, then the efficiency of that search for the nearest neighbor can be significantly enhanced. Okay. And in the radial basis function network, we have to decide the centers of the bumps. And one good way to decide the centers of the bumps is to represent the data, i.e. to organize the data into clusters and pick as a bump center the centers of those clusters. Okay, so that's what we discussed in the last lecture. We discussed methods, a very, very short sneak preview peek at unsupervised learning. And let me emphasize, it was in some sense unfair. Unsupervised learning is a huge, huge area. And we just gave it one lecture because we have to move on. But in that one lecture, we discussed k-means clustering, a very powerful technique for clustering, and we discussed Lloyd's algorithm. Okay? And then we sort of, moved to probability density estimation, a sort of soft generalization of clustering, and introduced you to the Gaussian mixture model, another very powerful technique for sort of modeling and representing and structuring the data. Okay? Now, unsupervised learning is important on its own, because you can get a lot of information out of a good organization of the data, but it's also important for supervised learning. Okay? So those are sort of the messages from the last few lectures. Now, let's start talking about neural networks. And neural networks are, in some sense, a biologically inspired learning model. And what better than biology to inspire us in computer science? Because biology seems to have gotten lots of things right. Okay? So let's start, with sort of, a brief sort of perspective on the history of neural networks. And yes, I show you a cartoon of a neural network of a brain, and think of this as the biological inspiration for neural networks. Okay, and indeed, that's sort of how the whole field started. Okay, starting about 1943 with the McCulloch and Pitt neural network. Okay, but really, neural networks started perhaps in 1958, with the Rosenblatt perceptron. Okay, and neural networks were dealt a blow in 1969 when Minsky and Tappert sort of revealed this XOR and the inability to sort of fit simple functions like the XOR, and also the inability to sort of easily generalize the Rosenblatt perceptron in a way that's easy to fit to data. Okay? And so, this blow basically meant that neural networks subsided and they sort of disappeared because we couldn't do much with them, even though they had biological inspiration. Okay? Round about the late 80s and late 80s, the neural networks in some sense were revived. Okay? And what changed? What changed was sort of the arrival of the multilayer perceptron in around 1986. The multilayer perceptron was sort of this generalization of the Rosenblatt perceptron, and we'll discuss the multilayer perceptron today, and its generalization that led to an ability to fit the data well. Okay? This what's called, the backpropagation algorithm. Okay? Around 1986, and neural networks at that point took off again, okay? Because now we had a way to sort of fit more complex functions similar to the XOR, and we had a way to do it efficiently using gradient descent, which is a technique we've already seen before in the context of logistic regression. Okay, so neural networks took off, and around the early 90s is for example, when I got interested in neural networks. Okay, and then again in 1992 to 1995, neural networks were dealt a blow. Bam! Okay, now it wasn't so much an algorithmic blow. It was more of a statistical learning blow, something related to the foundations that we have discussed. Okay, so as we will see with different techniques, some techniques come in, some techniques go out, but at the end of the day, you cannot avoid the foundations. The foundations are going to hit every technique equally. Okay? And how were they hitting the neural networks? Well, the neural networks were this sophisticated learning model that could easily overfit the data. So the promise of the neural networks was not being realized. They were overfitting like hell. Okay, and people were getting burned. And so neural networks gradually lost out and eventually got completely wiped out, in terms of popularity of use by, the arrival of this very powerful and very robust technique called support vector machines in the mid-90s. Okay. And we will talk about support vector machines later. Okay, so it's very robust and also, very powerful, so able to model all kinds of things, including the things that stopped the neural networks in the 1960s, this XOR and the inability to do complex target functions, which sort of halted the neural networks in the 1960s, was overcome easily with the support vector machine by combining this robust linear model. So it avoided the pitfalls of overfitting with the nonlinear transform, which we have seen before. So all the foundations that we have seen before came in the mid-90s and hammered the neural networks. Okay? But then the neural networks started resurfacing again around around 2005, 2006, with the arrival of sort of deep belief networks and the ability to sort of these new training algorithms for large deep neural networks that went layer by layer, and the concept of pre-training the neural network. And then they showed up with a real splash in 2012. Okay, when deep networks were used, to sort of classify, images. And so I'm showing this in the picture here from the Hinton paper in 2012. Okay, and Hinton recently won the Turing Award, basically he shared it basically for the developments of deep networks, and especially towards sort of vision. Okay, so here you see some test images, and the deep network has basically got it right. Okay, so for example, this red car is human classified as a grill because that seems to be the focus of the picture. But the algorithm says the most likely classification is a convertible, then a grill, then a pickup, then a beach wagon, then a fire engine, and you can see the rationale for each of those classifications. Okay, so there was this great success of deep networks for vision. Okay, and that sort of inspired a huge surge in the popularity of neural networks. That we can now learn again with neural networks in a robust way. Okay, which was the flaw before, and what led to the support vector machine killing the neural network. We can now learn, okay, and what changed? Okay, so. In the 1960s, it was the deficiency of the neural network that killed it. Okay? And what changed was the arrival of a new algorithm that allowed us to train, more complex neural networks on data, and so then it resurged. But the problem was overfitting, was inability to generalize to out of sample, and that's what killed it in the mid-90s with the arrival of the support vector machine, which solved that problem. Okay, so why is it coming back? So now we are able to sort of deploy the complexity of the deep networks, okay? Because of A, we can efficiently train them, okay? And B, okay? This concept of pre-training allowed us to use networks, huge networks trained on large data sets, okay? And then fine-tune them on the data set of interest. But most importantly, we now have lots and lots of data. That is the primary reason why we can get more robust to noise. Okay, we have lots and lots of data. So we train deep networks in huge databases, and then we can sort of transfer that learning to the domain of interest. Okay? And so neural networks are back. But who knows? The lesson here is that certain models may come in and go out, come in and go out. And at one time, the in thing was the support vector machine. And now the in thing is the deep network. But, if you are well versed with the foundations, you can understand why certain things come in and go out. And, okay, you can adapt to the changing landscape. And you know how to control these various models. Okay. So, that's a brief history of neural networks. Today they're very popular and for a good reason. As you can see from this picture, they're doing a reasonably good job at a task that humans do well, and they seem to be doing it almost as well. So neural networks have now become quite sophisticated for vision, and they've infiltrated into all kinds of other areas: speech, natural language processing, all over the place. Okay. But it's very important not to use them blindly. So that's what the sort of next set of lectures is all about. We're gonna get into the nuts and bolts of neural networks. Okay? And as you will see, you cannot avoid the foundations. So you have to deal with the E-in issue and the E-in versus E-out issue. Okay? And it is the fact that these two have been to some extent dealt with that allows neural networks to be deployed at the scale that they're deployed today. But if you're going to deploy neural networks, you need to know how to control those two steps of learning with this very powerful, machine learning model. Now, when we discussed the linear model, we said that you've got the linear model, it's a sports car. Now you add on to the linear model the nonlinear feature transform, and it becomes an 18-wheeler. Very hard to stop, very hard to control. It just eats up the data and overfits. Okay? And so the neural network is, an 18-wheeler squared. Okay? So you really need to know how to handle these neural networks. Now it is true that you can download packages, and they dealt with things like regularization, and they implemented various basic things for you. Okay? But you still can't take even a downloadable neural network package and apply it to a 1,000 data point data set. Okay? You'll just overfit like crazy. You need to know how to choose the architecture of the neural network. And you need to know why it will work and when it will work. Now, to some extent, we haven't fully understood those issues, but one of the things we do understand is that they work best when they have been pre-trained on huge data sets outside, okay, in order to sort of extract reasonable, representations of features at different levels, and then the final level features are ultimately what are combined as a linear model. Okay, so in a nutshell, neural networks are combining linear models in a cascade fashion, okay, and that cascade fashion of combining linear models gives a huge amount of power, and that's what we're going to discuss today. And in discussing the cascading of linear models, we're going to derive the multilayer perceptron. Okay, before we get going, let me just sort of take with a grain of salt this notion of the biological inspiration of neural networks. In the early days, yes, the neural networks were biologically inspired, but today the neural networks are built in a different way. They are built for engineering success. They're built to get E out small, and so they don't look really anything like the biological counterparts, and that's okay, because what we care about is engineering success at the end of the day. Although it's nice when you can sort of get inspiration for biology. And now here's an analogy, birds fly by flapping wings. And that's what inspired us to fly. First, that it's possible. And second, gave us some hints as to how to do it. But we tried in the early days to flap wings. It didn't work. Engineering success has resulted in the plane with jet engines and so on and so forth. So we don't flap wings to fly. And that's driven not because we don't want to be biologically inspired, but because at the end of the day, what matters is the engineering success. Okay? And so we'll bear that in mind when we're building our neural networks. Now, let's start talking about the multilayer perceptron. In particular, let's start with the XOR problem of Minsky and Papert that led to the initial downfall of the neural networks. Okay, so basically, they revealed that the linear model, the perceptron, has a real limitation. This XOR function, which you think of two lines crossing, and opposite regions are the same classification. So opposite blue regions and opposite red regions. Okay? And if this is your target function, it's relatively simple, but there's no perceptron that can come anywhere close to this. And you can come up with other simple target functions that the linear model cannot do. Now, we try to address this with nonlinear transforms, but you'd need a very contorted nonlinear transform in order to implement this. Okay, and what we're going to discuss is another very simple approach, okay, that will not only allow us to do this XOR function, but it'll open the floodgates. We will essentially be able to do anything. And what's that simple approach? The simple approach is instead of is to cascade the linear model. So it's still the linear model, but we're going to cascade it. Now, let's first start by showing how cascading of linear model can allow us to do something like this complicated XOR function. Okay? And that'll lead us to the general multilayer perceptron. Okay? And we will then build sort of the general notation for neural networks and show how we get in a very simple way from the multilayer perceptron to the neural network. Okay? So the main goal today is to sort of demonstrate the power of cascading linear models. Okay, and then take that power and build the multilayer perceptron, okay, and introduce the notation for the multilayer perceptron and ultimately for the neural network, okay, as a very simple extension of the multilayer perceptron. Essentially, the neural network will be the multilayer perceptron, but made more convenient so that we can run algorithms, okay, in particular gradient descent. Okay, let's get going and let's go to the board.